Talking last time after divorce was hard, but I realized that talking before divorce is also difficult. So there's no way to have to anything, okay? Anyway, but I'm gonna just do it. So I thought I would do something different, which is to talk about the general problems of drug discovery, whether you want to do an active or a small problem, or whatever, because I've been thinking about this problem forever. And
I don't understand. Starting again.
okay, thank you. So, here is the problem for drug discovery, independent of modality. So you can read it yourself, because you can read. And the first paragraph says, we have all these different ways of making drugs. And it ends by saying, my goodness, this is breathtaking. And yet, the number of annual approvals in the US by the FDA is more or less unchanged. What does that mean? What does that mean? So it says, you've been thinking about this forever. How come there are more failures than successes? That's the question I would like to address. And this is a reminder for those of you who never developed a drug. I've been part of developing one once, which I had almost nothing to do with it. I just watched. But if you're close, you should learn a lot. And these are the steps that it takes to develop a drug. And you've all seen this. And because we are so focused on basic science, this group, we forget all of these steps because we're busy developing technology. We've got to find a protein that's a good target for the disease you care about. Then you do all this thing, 2, 3, 4, 5, and 6. And it's only when you get to 5 that you actually know if the choice you made in the beginning is any good. $30 million later, there are people that argue whether it's 10 million or 30, it doesn't matter, it's a lot. And in companies, when you, as a basic scientist, say, hey, I think the target is TGF-beta for cancer, for example, there will be 50 other people competing for the same money, they're just as smart as you are, they're just as nasty as you are about fighting for resources. And so in the end, even if you win the money to try it, the chances of it succeeding at the phase 2 pivotal clinical trial is low, because finding the right target is hard. So that's what I want to talk about. Because we have one example, only one that I know of, in which we've been, I think, successful at figuring out a target before you work too hard. So this is a reminder why we worked so hard for the last years to develop SomaScan. It's to make biomarker discovery easier. And you all know this, the Boyce's talk, which I saw the other day, is spectacular. See everything. And then the fourth point is the problem. When a biomarker goes up in some disease, your brain says, that caused the disease. And that's bullshit, okay? But common. And even when you know it's wrong, you say it anyway, okay? Because it makes some sense. It's certainly plausible. that you have discovered a target, but it's much more likely you discovered a biomarker that doesn't do anything. It's a problem. I mean, Boyce and I had dinner last night at a wonderful restaurant. We giggled the whole time because it was called the Giggling Squid, and it's just a great restaurant this time. And we were talking about the example of lung cancer, where you have a tumor and you have healthy tissue just outside in the lung, and people have compared the two for transcriptomics and proteomics. And there are, I don't know, 10% of the genes are either overexpressed or underexpressed. That did not give you a target, because this is about the dimensionality of the choice. It lowers the number of things you can think about from 20,000 to 2,000. That doesn't help. So you got to do better. All right, so this is funny. So this is a slide that I raced through the other day. It's my favorite slide ever made. I have no reason to be showing it to you except that I get to do it before the boys. Take what you get. In the this is a co-crystal structure of a somamer, the green thing, with its protein target. And before there, in that version, if I asked you, this knowledgeable group, to choose whether it's a green thing or a white thing, it's a somamer, you would get it wrong half the time. This, never mind graduate students, because they look the same. They're both globular things. So that's the beauty of that. And so I'm wishing you can just do the best you can. So we built SomaScan, and all that matters is how now use it. All that matters is what's written. The present version of SomaScan measures 7,000 proteins. It's available. It will grow in the next year to 10,000. All of those somers already been made. So it will be a 10,000 device. The CVs are great. Almost everything. Not everything. Those things. It's not big. It's eventually big range. So you can do the proteome today. Certainly here. And the arguments that's enough. Arguments we should finish it. The arguments are stupid. We have them. And because it's worship, I'm saying sonologic is not understand anything about science. It's a real so let's see. So on that proteomics platform, we've run about 600,000 samples, largely from plasma serum urine. But what it doesn't say, it can also do tissue. We can take a chunk of tissue, line it up, and use it. And that's what I'm going to end up talking about. Lots of collaborators, sometimes they're called customers, that's how it's the same to me. You don't need to hear my views about cancer biology. You also don't need this slide, which I showed the other day. These laugh to they're ahead of last time I showed. This is one of my favorite slides ever. Because it's true. You know so my email address was at the beginning. If you want these slides, so crazy just want them, send me an email. I'll send So I want to now switch to the one example we have where we helped this guy, Scott Phelps, from the top of this to do the thing he cared most about. So I'm going to tell you a story about a new company called 10-0, which is a company that Scott started based on some skin work we did for him. And it's one in which, as you'll see, many miracles happen. And the miracles that are likely to be the thing that shortens this time to the pivotal phase 2 trial. So that's this slide has a lot of information. He's a friend, he's been a friend for 10 years. He's from Denver, not Boulder, like different countries. And he's a neurosurgeon, Scott Phelps. And his job in life as the chief neurosurgeon at a place that specialized in spinal cord injuries was to be the first surgeon to save the lives of people from car accidents and from other sources of spinal cord injuries by operating on them so they didn't die. And we all learn a lot of nutrition doesn't well at this point. 10% of the people who have spinal cord injuries in the United States got them from tripping over their dog, walking into their study at night to say goodnight to their husband. The real number from Scott Phelps. It's an anecdote, but scary. It makes you not want to open it or not have the study time. There's nothing funny about this stuff. This is all stuff. It turns out that the fourth bullet is the key because Scott Phelps, a neurosurgeon, cared about his patients and talked to them. Let me say that that's sufficiently unusual amongst doctors. I hope I've offended some of you. To actually talk to patients and ask them how to do it instead of just next. And he talked to them a lot, and it turned out that about a month or so after they had become from their accident paraplegic or quadriplegic, and he had saved their life by operating them, but not in a way that made them able to walk, for example. He realized, as it says in the fourth bullet, that the patients complained more about their pain than about the paralysis. But I learned this from him. He could have pushed me over with a feather because, and it turns out that about 80 or 85% of his own experience, patients with traumatic spinal cord injuries end up suffering unrelenting, enormous pain, suicidal pain levels that could not be helped by the painkillers that exist today. And it just bothered him. And so he discovered the source of the pain. He did resections and ablations of that source tissue. I'll tell you about that. And eventually came to us 10 years ago. It's been going on with Scott for a long time. To figure out the differences between the pain causal tissue and the non-causal tissue for the proteome, because he thought correctly as a neurosurgeon that we might have a path to drug discovery. And I mentioned before, again, a thing I learned from Scott, everything we know about this, we learned. The patients don't want anything done to them that might eliminate the chance they will walk again. And they say it in ways that are just so sad. They say things like, I want to walk my daughter down the aisle when she gets married. when you hear that, it's heartbreaking. And so patients would rather have a drug than a surgery that might do damage to their spine. Again, something I would never have understood, okay? So here's a key paper, there's a reference, you can read it. He discovered, Scott, he's the first author on this paper from 2018, that if you had a spinal cord injury, including a severing of your spine, so completely eliminating neural transmission into your brain, gone from the spinal column, you could have, and this is, as I said, at 80 or 90% of the patients, severe intractable pain below the level of the severing. So you don't even understand that. It's often called, you know, because I'm a biochemist, I'm not about medicine. But you know, you've heard about this for people who have had a leg amputated. They feel phantom pain and missing leg. Total mystery. No one understands it. Zero. And this is similar because there are people who are paralyzed from the neck down who feel intractable suicide level pain below where they don't feel anything. You can hit them with something bad on the leg. They don't feel anything because they really are paralyzed. And then they can experience pain, constant pain on the same leg they can't feel anything. It's a remarkable piece of biology if it wasn't so sad, right? I mean, this is really horrible. So he found, as it says in the fifth bullet, a part along the spinal column in these patients below the breaks, below the injury, that were hyperactive electrically. I'll show you that. This is the story. And with the consent of patients, he was allowed to ablate the electrically active tissue. And shockingly, when he did that, 85% of the time, it's the same number as the other, but they're not connected. 85% of the time for hundreds of patients, the pain went away. Holy moly. A neurosurgeon figured this out. So whatever I said to dump on MDs, I'm not using to dump on him because he was a genius. I'll show you what that looks like. So using some gizmo or another, if you look for electrical signals along the spinal column of a person who's been paralyzed by a spinal cord injury, you don't see anything. If you look at these things, they look flat, measure something or another, measuring purple and green. That's how much I know about electricity. That's good. And the thing in the middle actually is a heart. So it's not, it's a heart. Scott said to us. And the region that he's going to focus on is this thing called, which nobody in this room has ever heard of, unless you're a lot smarter than me. I've never heard of this. It's called the dorsal root entry zone. And that's where there are nerves coming out of the spinal column and going into other nerves that are outside the spinal column. So it's a way that you can have neuro talking between the spinal column and the brain and the outside. And the thing he observed is right there. The one on the middle is what I just showed you. And the one on the left is the thing he found. He found hyper-electrically active thing in the same place, just a little above or a little below, same kind of tissue. And this surprised him. And he made a stunning observation, same guy. He's kind of 1 for 3 for 3, or he's an amazing man. He made the observation that the location of the electrically hyperactive tissue was the same in different patients who experienced pain in the same place. That kind of an amazing, it was like being Darwin or something, just paying attention. And so if you had pain in your left ankle and you were paralyzed from your neck down, you would report that, and the paralysis was clear. If you had a high spinal cord severing event, and you said, my left ankle is just killing me, he would find this place of hyperelectrical activity, not down near your left ankle, but somewhere along the spinal column. The same for every patient who had left ankle pain. Remarkable. This is like, wow. So he was ablating. The patients were getting better from his ablation, and then he listened to his patients over and over and over. That's his MO. He realized that it would be better to figure out a way to treat pharmacology. He came to us and said, I can resect patients who get better because they send permission to take similar looking tissue out, just above or just below. Couldn't use some scanning and figure out what's going on. His idea. He had previous consultants. We helped him. Here are the things. So this is the most important part of this talk. Time it says 12:04. It's not. So this is a volcano plot of data from Scott's samples. And the way the data are shown, to give you this red box, which is the focus of this discussion, is that each dot represents, in this case, 5,000 protein. So it's confused. One patient is 7,000 plus, 10,000 plus. This is from the flex. And the points for each protein are the ratio of the protein measurement in the electrically hot tissue divided by the protein measurement in the cold tissue that was adjacent to it. So that's, you could do the same thing for cancer. We've done that for cancer, exactly this. And you get 10% of the proteins would be in the red box, 5% in the red box, 5% on the other side, downs. And it doesn't help much. But some combination of this work and what Scott did next, which I'll tell you in a minute, is miracle after miracle. So in that red box of proteins overexpressed, present in the electric hot tissue, one real place to solve the pain or seconds. There are 60 proteins, and his focus then became which of those 60 proteins might we use as targets to turn off pain? It was from the pain causing tissue, so it was a logical. And he read about all these 60 proteins, which is a lot. And among the things he and we discovered with him for him was there was one that's labeled Scott's First Hope, a protein called SV2A. And if you're like me or Navisha, I never heard of SV2A. And probably no one in this room ever did either. Why would you hear about any protein? You hear about a human, you hear about things you don't know. If you work on aptamers, you hear a lot about that's an aside. And he decided that SV2A is the first thing to try a non-surgical drug-mediated release of pain. And he did that because there's a drug that was aimed at SV2A already. So in a sense, this becomes a little bit about drug repurposing. So of these 60, about a quarter of them have drugs already. And in the United States, you're allowed, with the consent of the patient, to treat. Sometimes you have to pay for the drug, but insurance companies. This is an experiment done with a willing patient who has suicidal pain. Insurance companies ought to pay for that. They don't. But this was Scott's first game. So the drug, there it is. That's the drug that was aimed at SV2A. It's a small molecule, orally active. It's called Briviact. And he did in his compassionate use study 8 patients. Oh, what's going to happen? It could be that of those 60 proteins, or 15 drugs already, that they were all correlates, not causal. You understand the question? That is, they were in the red box, but not driving treatment. And here is what happened with the first 8 patients. Now it's a bigger clinical trial. And the first 8 patients, 5 of them had relief or pain from the drug, not with surgery. I would say in the list of drug things that unfortunately I read about, this is a little more. So I mean, there are very few drugs that work for 5 out of 8. Period. That's in itself a very high number. I mean, for cancer patients, the quarter is considered. And so this was grounds for Scott starting a company, this company called 10-0, which now is in the process of raising money. But you would think you'd be nervous about this one. And so he tried a second. This is painful. I hate secrets. Except for my first one. Just on this side. He picked another target. This was a target where the drug was a monoclonal antibody. So presumably an extracellular target. Stop this. Stop everything with my mouth. But I think there's only so he tried it. One patient only, as opposed to 8, now 20. Yeah. And he did it in a way that was fair, that he didn't promote anything. I ended up talking to a woman who's a chronic region who was in Craig Hospital. And it turns out that she suffered from, in addition to her paralysis, the very thing that this second was aimed at. And she had a condition that made it legitimate for her he was hoping was that it would solve whatever the medical problem really is that the drug is aimed at. And then it would reduce her pain, and it did. And it reduced her pain significantly. 8 to 10-point scale. These things are not rhythmic, from a lot of pain to very little. She can live a normal life, more or less, but still paralyzed. And she forgot that she had to get another dose because these things only last a month or so. And so her pain came back, and she went to her regular doctor, not Scott, and got another shot of a monoclonal antibody given systemically. And again, has no pain. So she's been now on this painkiller. So I want to show you 2 more things the boy showed hanging there. One is that we've spent a lot of time trying to help Scott understand pathways, because of course all these proteins that are in the red box are part of pathways of some kind of another. And so we thought maybe we'll learn more, so we're in the process of doing that. And here's so this is the last slide. And it's actually a slide that builds to the bottom point. So to me, the miracle is actually Scott Phelps. It's not SomaScan. In a way to measure proteins, and it hasn't led to drugs yet for anybody. Yet will, but it's a big pharma problem. The reduction of the dimensionality of the search for targets and drugs. And we've been doing a lot of talking to people who do artificial intelligence for years and years and years. And we've understood that in the early days of artificial intelligence, chess and Go, kind of things, that it helps to talk to experts. You'll learn from experts the way to think about the problem. Nowadays, that's not going to be the future. Nowadays, well, I love it when smart people go, yeah, thank you for that. Well, it's an area to think about. And we have an expert who was, depending on your point of view, 2 for 60, or 2 for 15, or 2 for 20,000, or depends on how you want to think about it. But if he's 2 for 2 is the most important thing. So we've decided, he hasn't seen the slide yet, that the thing we should be studying along with studying pain is Scott Phelps himself, because there will be lessons to learn as we poke at him. And we're going to do that. And someday, the boy or I will come back and tell you what we found in his brain. And that's the end. Thank you.